Hey guys, welcome to a tutorial video on Vo2max Analysis. So the first thing that you guys will need for this particular prac or lab assignment is your Vo2max Analysis template. And you will also need your raw data. So once you have your raw data loaded up, this is just an example for Joe's soap, is to go all the way down, select the T column, press Control Shift and right to highlight the entire dataset, and then Control Shift down. That will highlight all the data in that particular sample. Press Control C to copy it. Then if you press Alt Tab, it'll take you back to your other open sheet. Go to the Metasoft Studio tab, then click on here, right click, and then paste special values. Alright, so that's going to paste all those values from your raw dataset into here. Just remember to scroll all the way down to the bottom of your data to make sure that there's no leftover data from the previous test. Just if there is, please delete it. Once that's done, you're good to start your analysis from there. Go to the sheet 2, which is where you'll start. One of the questions it'll ask you is which row does your data set start. If you just go back to your raw data, or to where your data was pasted in, you'll see here at row number 126 is basically where all the information starts. So we can keep that at 126. Also, what was the final RPE of the test? So once you've completed the test, remember that you're going to log your final RPE value here. In this case, for this particular athlete, it was 18. The type of test, you can select between running and cycling. I'm going to give you guys an example of a cycling test without a validation bout. In that case, remember to add the age of the participant. This participant was 25 years old. The particular protocol was a continuous protocol of 20 watts per minute with a starting power of 100. You can change these, and all that information will be reflected in your analysis. Okay, one of the first things that you're going to look at is your VO2 VCO2 difference. Remember, the program's going to automatically show you where the RER value, denoted here by green, reaches a value of 1 and stays above 1. That's kind of where you want to move your gas exchange threshold line to. So if I just hover over here, you can see that the time occurred at 539 seconds. So I can shift this either using this the slider. That's too much. I can just backtrack it, or in the time column or row, I can manually enter it. So 539, and then that should take me directly in that. Remember, the moment that I move this, all the gas exchange threshold summary data is reflected in here. And we know that gas exchange threshold should occur at an RER value of somewhere between 0.95 and 1, that you'll have a pretty good confidence that that's the right threshold. Over here, just allow you guys to investigate the respiratory exchange rate ratio a little bit more. We can see here where the crossover point occurred, and the time is given here in minutes, and the lactate threshold time here is also given in minutes. So this is automatically identified from the data. You can just take a note of that. So where the RER value goes to a value of 0.85 and above is at 4 minutes, and where it goes to a value of 1.0 and above is approximately 9 minutes. And that's again what we identified here as well. You can also see that the workload here is reflected in terms of that continuous protocol of 100 watts as your starting power. Obviously, this is the axis for the workload. So it starts at 100 watts and increments by 20 watts per minute. Alrighty. The next one that we can look at is your end tidal volumes. Remember, again, you've got two sliders here, one for the gas exchange threshold and one for the respiratory compensation point. This data doesn't adjust automatically. You'll have to identify it from your knowledge of what the gas exchange threshold should be when you look at your end tidal values of PET-O2, PET-CO2. Again, you'll change where you think the gas exchange threshold occurs and where the respiratory compensation point occurs. So I'm just going to manually slide it up and down a bit. just to get an idea of where certain things are happening. Let me try and slide that up a bit, maybe a little bit more. And then respiratory compensation point, I'm going to shift as well. Remember, that's where your PET O2 typically starts to take a deflection down from a straight line. So again, I can use the slider, or you can enter it manually. So if I had to take this up 576, maybe that's might be a bit of a better inflection point there. And again, I'm just rushing through it. You'll take your time and you'll start looking at the values that are representative of the gas exchange threshold and of the respiratory compensation point in terms of things like your relative VO2, heart rate, RER, power output, so on and so forth. Remember, this is a cycling test that I'm giving you guys an example of. So remember that your workload is given in power, which is a measure of watts, or given in watts, which is a measure of power. If this was a running protocol, this would be velocity given in kilometers per hour, for example. The last one, you can use your ventilatory equivalence, which is your VE/VCO2 ratios. And again, you can move this using the slider, or you can enter the times a little bit more manually. So let's just say I go to this particular point over here, 476, see if that's any good for us, and then possibly over here 581, and these are just like some preliminary values that I'm putting in. You could go back and forth to find out a really good inflection point. Once you've done some of the other analyses, you can always come back here and change these values again. Alright, so if I want to identify the gas exchange threshold a little bit more, again I would come to the V slope page, which is looking at the VCO2 divided by VO2. Remember, you're going to tell at the starting and end point. So let's say 126 is where I started and I want to go to 150. What in essence you are doing here, what these numbers represent, is from your raw data, you're telling it, look at the data from row 126 to 150. I want to look at the VCO2 values relative to the VO2 values at that point in time, right? So your first regression line is just looking at that data, and it fits a line of best fit with an R-square value of 0.976, which is really good fit for those data points, and those data points are highlighted. Then there's a second regression line. So for example, if I wanted to fit a regression line through this data down here, that's what I'll put in here. So let's say I start at about a 151 and I take it to about 200. So you can see now it's highlighting those data points and fitting a regression line through those data points and giving me the inflection point between these two regression lines. Okay, that inflection point is then again represented here by the summary. Gives you the absolute and relative VO2 at that point, the heart rate, the RER, and the power output at that point. So what we can tell is that the RER, what we mentioned earlier, is that the gas exchange threshold should occur somewhere between 0.95 and 1. So you can see this is obviously way too low. So this represents the very, very beginning parts of the test, and the individual hasn't even cycled properly yet. You can see here it's at approximately 0.1 second to 1 minute and 14 seconds is where this initial data is looking at. So what I'm going to do is I'm going to try and ignore those first points and shift this up to 140, and then take it up to about 180. Remember, this is looking at the rows in the raw data. So now the time over which it's analyzing that is between 43 seconds and 2 minutes and 53 seconds. And again, that's quite low down. We can see if you look at all these data points, they accumulate relatively linearly, and then beyond that over here there seems to be a bit of an inflection point. So I'll include some more data in that. So maybe if I go to 250, and you can see now it's analyzing that data a little bit better, and this I'm going to shift, say, to approximately 350. Oops, 350, and I'll start at 300. See if I can get that. That's already looking a little bit better. So what I can do here, is I can include some more data points in this initial analysis. Again, I've got a slider in here that can just progressively increase it, and I can kind of keep an eye on what's happening to that R² value. If it's improving as I add more data, I'm quite happy with that. 0.969, that's going to be really good. And then over here I want to include some more data points in this later data set, and again I can use the slider to progressively increase that. That might be a little bit much, but excuse me. If I look at the RER values now between 0.95 and 1, that's looking a little bit better. And again, I would go back and forth and fine-tune it until I'm really happy with that inflection point in terms of the physiological data. In terms of my respiratory compensation points, again, you know, I can start the analysis at row 126 and go to 200. But we can see there that this is a relatively linear increase all the way through. So I can keep it where it was. I'll start at 140 because I don't want to include those first few data points. And then I'll go to approximately 300 and kind of see where that takes me. If I'm kind of happy with that, I can progressively increase that and include a few more data points. And you can see here this is dynamically updating the entire time. And then the same thing is true with the later data points. So I want to say fit a regression line at some later point in time, looking at these later data points. The maximum number of data points are 422, that's always given, and the maximum test duration was 12 minutes and 8 seconds. So that's also a guide as to the length of time within which that respiratory compensation point should occur. Right, it should occur definitely before 12 minutes and 8 seconds. And you can see here that the later data is being analyzed between 10 to kind of 11.5 minutes. Alright, and again, look at the R² values to see that the data is fitting really well with your regression lines. Again, it's taking some of the subjectivity out of it and putting some numbers to some of this data that we're analyzing. Last but not least, we want to look at the Vo2max. So you can see here's the VO2 data being plotted relative to time. Time here is just given in seconds. You can see here that the test kind of ends at around about, say, 720 odd seconds. And I've just given it some starting points here of 850 seconds. So I want to change that. I'm going to put in 720. So in essence, what you're telling it is to start the analysis at 720 and work backwards by approximately, let's say, 20 cells, and then it's going to analyze that data. I'm going to make it 710 because I don't want to include these very final data points. That's where the athlete might have completed the test. And you can see there's some pink data points here. That's what we typically use for the verification bout, but there's no verification bout done for this particular test. So I'm going to make these values equal those values so that I sit with similar data. Perfect. What you can see though is that these pink data points are above these green data points, and that's because our axes here are not equal. This goes up to 5, this only goes up to 4.5. So I'm going to double click on this right axis and just make it go up to 5 as well. Press enter, and now your axes are aligned and the data points are equal to each other. Awesome. So what the computer then does is it takes the average of these data points and tells us what the absolute Vo2max is and what the relative Vo2max is. Remember, relative Vo2max is the absolute value Vo2max multiplied by 1,000 and divided by body weight. So the really important component is to put in the athlete's body weight. Don't forget to do that. I don't want you guys to change it here. In essence, what I want you guys to do is go to the original Metasoft Studio tab, and you'll scroll up a little bit and you'll find that there's a weight section. You'll always have to enter weight to 3 significant figures, so 75.0 or let's make this 75.5. Please don't put 75.54 or whatever the case may be. Round it off to the nearest decimal point. Okay. And leave a gap between that and the kgs, because the computer automatically takes those numbers and puts it in over here. You can see that's now updated to 75.5. Again, if I change it here to, let's say, 68.2 and press enter. When I go back, it's going to be 68.2. Okay, so that has to happen in that Metasoft Studio tab. Okay, and then again the values are given here for us. There's also the criteria for Vo2max that you can look at. The heart rate max criteria for reaching Vo2max is dependent on the literature that you read, so I've allowed you guys to adapt it by just clicking on these specific cells and selecting what criteria you would like to use for having reached Vo2max. I'm going to leave it as is for now. So the criteria for reaching Vo2max is a heart rate at 95% of max. This person only reached 94, therefore that's not reached. A heart rate that is within 10 beats per minute. And you can see the person at Vo2max that we've identified here was within 11 beats, so it's also again not met. To have an RER that is greater than or equal to 1.1, and this person reached 1.23, so that is reached, and an RPE of at least 18, and the 18 was reached. So the verdict here is that we can be relatively confident that this person reached a true Vo2max. In other words, a plateau. Something that we can also check is the slope at this particular point in time, which you can't see now, but it's giving us a negative 330 odd moles. I'm still working on that. It's not final, so whether or not you want to use it, that's also fine. I've put in the criteria that you can use for Vo2max, but the computer's already given us ratings over here. You can change whether the participant was male or female. Remember, the age gets dragged over from across. The 58.49 is the VO2, the relative VO2 that was identified, and that has a rating of good. You can always double check that. A 25-year-old male of age, what did we say, 25. So if you look at the male rating for a 25-year-old of 50, what did we say, 58.9, so that's good. And that's exactly what we have here, so awesome. Alright, then we just have to do some final adjustments here. Remember, we had all those different methods of identifying the gas exchange threshold and the respiratory compensation point using end tidal volumes, ventilatory equivalents, or different slope methods. It will give you the different values that we have identified, the heart rate, the RERs, and the power outputs at those specific values. Again, this is where your knowledge of the physiology becomes really important, and which method you thought was most accurately reflective of that particular physiological point. So over here, I'm going to go with the V-slope method. So remember, these values are the values that you see here. So I want to pick that value, and that in essence is 83.2% of VO2max. Again, is that normal? Is that expected? Again, that's where your knowledge comes in. The respiratory compensation point, again, I will use the slope method there and use the 56. That's occurring at 96% basically of VO2max. And then the RER value, end stage value of 1.23 is rated as average based on the normative data that we are using. And in essence, that's what you would have. Then there's a report that gets generated based on all of those values, gets dragged across. I haven't fixed this because I want you guys to put it in manually as a summary together with all their values and what all of that means. There's also a summary training report that you guys can then use based on those, remember those RER values of crossover and gas exchange threshold, or here with your inflection points. There's different ways that you can prescribe training programs, training zones for your individual athletes or patients, whoever you want to try and increase the physiological fitness for in terms of their aerobic fitness. I hope that makes sense and it's kind of highlighted how to use everything within the program. The goal is now that you guys use your raw data and start analyzing it from there, generating the programs, and then that should be it. Hopefully that makes sense. Remember to read this in conjunction with the guide, because that will tell you a little bit more about the physiological underpinnings of ventilatory equivalents and end tidal volumes, so on and so forth. Right? This is merging the literature, merging the theory with practical application. Thanks for listening.